Hey, welcome back to the last crazy installment of Gaian Earth. This is meant to be the last of the new material, last lecture of the new material, probably followed with a recap of the term's overall 10 weeks of material, go over a bit of the calendar of events, and then some smaller random bits. But really, this is the last overall of the course. This is the last topic that's meant to be discussed in the final exam and things like that. So what are we up to today? I like to call this our look at our Gaian planet. If you recall, we kind of started the course in discussing this as our violent Earth. And today we're going to, look at our species as we started to in the last lecture and the Anthropocene, and overall look at the, again, not the human violence that we exhibit towards each other, but instead this great natural force, this geologic force that we, as Homo sapiens, now exhibit here on this Earth. It's pretty interesting and pretty intense, but I have some good positive notes on the end of this, okay? Not sure about you personally, but oftentimes it's my experience that this kind of brings out two major camps or bimodal thinking in people, right? Either you have kind of the one extreme side of holy cow, look at what we have done to the Earth and to the planet, and we're sort of making our own bed, and we are ultimately in some sort of demise and extinction, right? Now, that's very extreme. Again, this is something we're talking about in the future, so nobody can tell the future. But that's an extreme way to look at our situation. Then there's the other extreme, I think, which sometimes takes it a little bit too far as well, is the discussion that everything is fine. Yes, we've done all of this, but it's all fine. We're going to find a way to get out of it. We can invent some, silver bullet that's going to save us from everything, and just don't you worry over there. And really, those are two very extremes. Yes, I want to end on some positive notes, but really, this takes work. This has taken work to get to this position that we are in here as a species, and with the rest of our species of brother and sisters on the planet. By that I mean all the plants and animals, bacteria and fungi. It's taken work, and it's taken quite a long time, not geologically, but a long time generationally as humans to get to this point, and we can't escape it overnight either. It does take work. It takes perseverance. It takes discussion. It takes changing philosophies, minute by minute, day by day, acting on these things, as well as acting with multiple generations, right? The parents in front of me, my grandparents, then my children, and my children's children, right? And that's sometimes what's thought of as the proverbial, multiple generations of thinking, 5 generations. Now, just wanted to bring that out immediately and to say that we really, we have hope, but it takes work, okay? So we can not just put it in the hands of technology and not just throw our hands in the air and say, oh, we're all screwed, but instead we can collectively, using knowledge and action, make progress together. All right, so let's head back for a little bit of recap here. No, I don't have a spiral today. I don't have a spiral of events. So after the discussion on the Anthropocene the other day, I like to ask the question, sort of a self-reflective question, is the Anthropocene as a term, is that synonymous with an age of environmental awareness? About a decade ago, when I'll answer the question in a second, just hang on, hold your horses. About a decade ago, when the word started to become kind of more in use, starting in academia first, and then kind of bleeding its way into the geologic community in academia at every level of geology. This was at least how I interpreted this timeline. And then, of course, the environmental community. I don't know exactly what that means, but just the idea or the concept, the collective understanding of environmental awareness and energy, peak oil, things like this. The environmental community, I think, did latch on to the word Anthropocene and used it in not really what the word is meant for, but used it in a way to kind of collectively point out that we are in both a time of, that this is in a time of environmental awareness, it's a time of environmental destruction, and that humans have dominated the planet, and we are naming this time after ourselves, kind of egotistically, out of this sense of environmental awareness. Now, that's not exactly how the term is meant to be used, though it is being used that way in the environmental community or in social communities, right? And so it is being applied that way already. And I am not necessarily opposed to the use of that term in a way to invoke, almost kind of invoke some motivation in ourselves, right? That humans in our time here on this planet, very 3.5 or 4.5 billion years long of this planet, and then another 4.5-5 billion years yet to go. We are certainly in the middle of this time where we've done enough in this environment that we are recognizable in the future, right? To future geologists is the kind of thought frame. Even if there aren't geologists, or maybe there are alien geologists or something, the idea here is to think about what geologic strata we are leaving behind. That's the idea of the Anthropocene, scene, right? Like Holocene. It's a geologic time period that is meant to be exemplified by whatever was going on geologically at that time, and it happens to be humans because we're the dominant geologic force of the landscape. Okay, I don't necessarily have a problem with referring to it in that environmental context because, boy, we need something to rock us awake, right? This is a time of environmental awareness. This is a time, the last couple 100 years or 100 years of environmental destruction in the industrial age, and we'll look again at those graphs of the Great Acceleration and talk a few things about a little bit about that. But I really don't think that's a problem. We need to be motivated. Again, like I was saying a second ago, there's the two extremes, but it takes work, and we need to be motivated if we really see our future, the longevity of the human race, threatened. Certainly, the lifestyle that we live with today is certainly being threatened under a very short couple of generations. And whether that's happening with resources, as we'll discuss a little bit, or the impacts of climatic change, global climatic change, my children, and of course my children's children, will inevitably deal with the consequences of this time, the Anthropocene, or the sort of pre-Anthropocene as well, leading up to this. So I do really agree and see this as a great motivator for us to talk a bit about those collective ideas of environmental awareness and whatnot. Okay. Okay, had to stop the video there. It gave me the almost dead warning. So wouldn't you have it? Get everything set up, and then you almost might, the video might not happen anyway. Okay, back on the horse. It's true that we are we are aware of our impact on the Earth and the environment. And the Anthropocene, though, is a stratigraphic marker bed geologically that may lead some of us to seek sustainability, but clearly not all of us. And I think that is part of the idea in the generation that we, of young people that we live in, now, well, not just young people that we live in, but what might be classified as sort of the millennial generation that tends to be a bit more environmentally aware, very tech savvy, very knowledgeable of our situation here on this globe, and then many generations outside of that are not necessarily using this as a motivating tool, but it certainly is, what do I want to say, it's economically impactful. And I think the implications of the economy as we known it, or as we've known it for the last 100 years, 50 years, 40 years, whatever, relatively recent, the economics don't project forward very well. And I think that people of older generations that are really that are adamant for progress to continue in exactly that same way, what I know is what will be applied in the future. I think that many of those people find this a very difficult concept, right? This is the generation of climate deniers, the folks who are just, digging their heels in at any sign that we as Homo sapiens are degrading the environment to a point that it begins to reflect back on our economics, and we'll have economic downturns at the whim of our own environmental problems. So certainly this does not work for everybody, right? This terminology, the idea of environmental awareness, it does not work at all levels, and that's something we need to think broadly about. So where we're going here, what is actually recorded in the rocks? What has been recorded in our history as Homo sapiens, and that would be kind of an archaeological record. What can we learn about our presence on this planet? Then what will be recorded as far as this time going forward? So a way to think about that is, well, what does our time look like geologically, right? Again, we tried to reconstruct times like the Devonian. What did the Devonian landscape look like? What were creatures doing? And then how did that lead to a mass extinction? And similarly, with any time in geologic history, we're using the rocks and the fossils, right, to understand something about what was going on during that time. And that's what we refer to as, what does it look like geologically? So what does this time look like through a geologic lens in that way? And then I guess another way to kind of think of that is, what is our legacy, right? Legacy is not something that existed in geologic time. The trilobites weren't like congregating in a building, trying to think about what is our legacy and what kind of rights do we give other trilobites. And what are they leaving behind, and are they the dominant species of the planet, and will they continue to be the dominant species on the planet 2, 3, 400, 500, 1,000 years from now, as I believe is in our collective desires, in a weird, funny way to say something about that in the future, that we expect to be around for another 1,000 years. I know that sounds I don't know, maybe to me it sounds kind of funny and interesting, but remember, only 1,000 years ago, right, or only 2,000 years ago is 1 AD, right, the beginning of the calendar that we use today. So 1,000 years, well, we've already done multiple of those thousands of years that we have record of. So why should we think in any way that we don't expect to be around in another 1,000 years? Clearly, things will change a lot, as things always change. They've changed since 1,000 years ago, but I think it is not necessarily in our collective, everyday thinking of the longevity of our species. 1,000 years is a long ways away. 200 years is a long ways away. Heck, 100 years is a very long ways away when we're thinking in the scales of quarterly profits every year. We run our lives on seconds, on minutes, on days, weeks, sometimes years. Even, thinking about what I did last year is like, wow, that was forever ago. So much has happened since then. We live such fast-paced lives in every day that it is almost inconceivable for us to think about the longevity of our species in 200 or 500 years. And at no other time in the past in our species do we really need to consider that very seriously. Because 1,000 years ago, even if they didn't really need to think about 1,000 years down the road, because the resources that they were using, they weren't using at a rapid enough rate to have an effect on us 1,000 years later as far as those resources that were being used. They didn't deplenish any resources globally that then us 1,000 years later we couldn't use. And so that's part of the discussion is what is our legacy as far as the resources that we consume and we make unusable for those in the future, or or what we leave behind as a usable environment. All right, so some of those things that have already kind of been addressed of what do we find in the rocks, right? What will be left here in the future? And I brought this up the other day, and you might have thought I was joking, but chicken bones, yes. The domestic chicken rose to define the Anthropocene as maybe a key fossil evidence for the human-influenced epoch. So there is an argument that over the last 70 years, chickens, a species from I believe from the mountains around the stands in Kyrgyzstan, maybe native to northern Iran, I believe from the mountainous areas in the Middle East, this bird that has spread circumboreally, and we have millions of these things every year are slaughtered and eaten by us, and it's their bones, fossils, that may be the dominant fossil in the Anthropocene. And then the timing is pretty right with the rise. We talked about the Trinity experiment being maybe the kind of marker, the chemical marker for the Anthropocene. And this certainly fits that timing pretty well. So you can correlate both the chemistry and the paleontology, the fossils that are showing up. Then another one over here, different than chickens, is plastics. Again, mentioned the other day. When plastics show up, that's pretty well about the time the Anthropocene is beginning. And so here's all of the types of plastics that you would be able to find as the stratigraphic indicators because of their low ability to biodegrade. So here's the beginning of those types of materials that are being manufactured. And then here we are up in the 2000s to show that, most of these things are still being made. PVC pipes, starting somewhere early 1900s. It was around, but it wasn't until the 1950s that this became a widely used material. And then that 1950 marker is pretty well shown, or is shown here, and it pretty well intersects with most of the beginning of most of these plastics, right, or most of these polyurethane materials. So again, 1950, a little bit earlier, being a good age or a good stratigraphic marker, supported by all of these polyurethanes as well. Then where does this stuff go? Of course, it's not just that, that stuff is invented in 1950. It is the presence of that in the rocks, right? It's the presence of that stuff in the geologic history. This is a model of distribution of microplastics. So microplastics that are, things that go through the washing machine maybe, or things, fibers that are in the washing machine that go into the water, and they slowly degrade is probably a poor way of thinking about them, because they don't degrade. Instead, the molecules become smaller and smaller and smaller until they become micro size or microplastics. So this is like cutting something up to a really small bit, and then these microplastics float around in the water column. And of course, it's the microplastics as well as macroplastics that become a problem for creatures in the ocean. The microplastics are actually more often eaten by plankton and smaller creatures, which then move their way up the food chain, as you can imagine. So this is an estimate that shows those areas in the ocean where millions of metric tons of plastics and their origin sites arise from. So where are all these plastics coming from? Okay, so that's a good, interesting article, and it shows all of the rocks that are being deposited in the ocean right now, or sorry, all of the sediments that are being deposited in the ocean now that will one day become stratigraphy or rocks, will carry the signature of the Anthropocene in all of these microplastics. So say that microplastics plastics stop being manufactured today, they go away. And then maybe in 50 years, all of the plastics that you and I use today in our lives, we've disposed of all that stuff. It's either in a landfill or it's gone down the river to go into the ocean. And then maybe 100 years after that, all of the plastics that were in the water column have now sequestered at the bottom. So what I'm saying is at some point, conceivably, if we stop using plastic, but if plastic was stopped in the environment, then there would be the time before plastics, whoop, the time of plastics, whoop, and then the time after plastics. Whoop. So it's a pretty good stratigraphic marker bed if it was to ever go away, right? Okay, those are two good examples of what we would find in the rocks that do exemplify the Anthropocene as far as the fossil remnants. Now, remember this slide, I'm bringing this up in a slightly different context now to bring up kind of archaeology, what is in the rocks that are already deposited that give us record of the past leading up to us. And remember that through anthropology, physical anthropology, and archaeology, we know a lot about not only ourselves, but our other brothers and sisters of hominids that were out there during the end of the Pleistocene. So certainly there are a lot of other hominids that are out there, but I bring this up now because they all met their demise, right? Or we're the only ones left. And there is a common argument that suggests that part of our behaviors are, and this is exhibited in war, essentially, of warring with one another, or of being scared of people who live on the other side, another border. Maybe they have different customs, they have a different culture overall. Maybe they wear different hats. You know, we do have some of this collective geographic fear of different populations, and it's thought that it may be a genotype that's exhibited as that fear. It's one of those fear-tingling things that is really ingrained in us from our fear of sort of an other, right? Any sort of other. That there is some sort of a there is some sort of an ingrained fear in us, or a genetic fear that is set off by looking at something that looks moderately like us, but is not the us. And the idea has been put forward that most of these species, if we came into contact with them, that fear led to potential conflict, or at least it increased the ability or the possibilities for conflict, and that at least some of these other 22 species, sister species, maybe met their demise at our hands. Now, nobody's saying that we went around slaughtering all of the Neanderthals or all of the Heidelbergensis or any Homo that was out there, right? The idea just has been put forward that we were potentially the insult to injury, right? If these creatures were already meeting their demise because of climatic change or genetics or environment, food scarcity, a whole number of reasons why species go extinct, but it has been suggested that, and certainly was suggested this way with Neanderthals for a long time, is that we hunted them to extinction, or I guess there's no better way to say that, right? That we hunted these Neanderthals, Homo neanderthalis, to extinction, and possibly others as well. So I bring this up to suggest that, or to look at the rock record, or at least in this case, the archaeological or anthropological, physical anthropology record, paleontology, to show that we've had an impact on this planet for quite some time. And we've already begun reflecting on that in these types of sciences and asking these questions on how long have we actually had this impact, and how long could you tell if we call today the Anthropocene back to 1950, well, is there other ways you could tell of humans' influence further back? And arguably, absolutely, right? We just showed one, the rise of Homo sapiens, and then the global spread also lines up very closely with the demise of all other hominid species, right? Then also you have the megafaunal extinction overkill hypothesis. This is old now by this point, and there's actually quite a bit of good data to suggest that this wasn't a blanket thing. Okay, now arguably in some areas, some land masses, I think like Australia, it is absolutely shown and been demonstrated that we can essentially blame this on humans, right? The extinction, 86% extinction of the megafaunal is pretty darn closely related to the presence of Homo sapiens. So megafaunal, these are big beasts, big animals, right? And a good hunter or a good team hunter, pack hunter like Homo sapiens as they became and began to spread across the world, when they spread to areas like Australia, and then found these gigantic beasts, of course, they figured out ways to hunt those things and to get a lot of meat to sustain their population and to grow their population. So it's no wonder why this occurred. And it was probably the hunting methods that led overall to the extinction, because they weren't selective hunting methods, right? This wasn't like, hey, there's an old male, let's go after the weak one. In many cases, these were mass events, like mass cliff running events, where the mammoths or bison were run over cliffs in droves and then were harvested later. Now, that's not the only way and the only technique, but you can imagine how a technique like that can be very devastating to a population when the entire population is run over a cliff, right? How can the species rebound and come back from that occurring multiple times a year for multiple years? So I do want to say, though, that there has been evidence not just to refute this, but demonstrating that this isn't the case everywhere. So some North American megafaunal sites and archaeologic sites have been, there was an attempt to correlate these to one another, to look for the overlap between where the species are actually going extinct, where we stop seeing the species, and if humans were near that area, right? Archaeologically, if we actually find evidence of humans in those areas. And there's a study that shows that, hey, these things are completely separate. So maybe these humans weren't actually hunting the megafaunal beasts in North America and leaving them alone, but they were meeting their own demise naturally as a natural. Remember, every 2 out of 5 species go extinct every million years. So after development, so maybe those species just would have gone extinct anyway. Things like the horse or the mammoth here, the woolly mammoth, Columbian mammoth here in North America. So this is another example of looking back in the rock record to see how have we had an impact on this planet. And these 2 last examples are biologically. Biologically, we have caused extinction in the past, the Holocene extinction of other species like us or other megafaunal species. Now, again, not all, but this is known to be some. So then there's also been plant extinctions during the late Pleistocene and the Holocene, and of course now into the Anthropocene. This is a good paper that kind of dives into the extinction rates of all of those things. It's been estimated that 4,200 species of mammals, 8,500 species of birds have become extinct since 1600. So this is well into, we're not talking archaeologically anymore. We're talking, after discovery of the New World and expansion into the Americas from at least from the Europeans. Now, of course, the indigenous being here already as well. So this is also compelling to show that this is a continuum from the Holocene from the Pleistocene, Holocene, and now into the Anthropocene, that the trend biologically is decreasing biodiversity at the hand of things like agriculture, urbanization, and globalization. So here's another modern impact, and so those were 3 examples that were dealing with the biosphere, how humans have perturbed the biosphere and have really changed things in that sphere, our own sphere of living. And then we could pick up on that geologically by looking at the fossils. But another effect, I find this really geologically interesting, we've also changed the balance between the atmosphere and the geosphere. The human impact overwhelms a long-term climate control of weathering and erosion in southwest China, suggesting that the natural variation of weathering and erosion that's occurring in China, that now human impact overwhelms the ability for long-term weathering and erosion. So not that we've stopped this or anything like that, and it's gone lower than us. No, instead, now we are the major erosive and weathering force of at least this province in southwest China. Another human impact that has an impact on the geosphere is the phenomena of a delta. So a delta is a region where a river runs into the ocean or into a large body of water. So rivers tend to be high energy environments. I mean, take a look at the flood material that we talked about a couple of weeks ago. But they tend to carry a lot of particulates. Floods could carry boulders, house-sized boulders or something, right? But even little small streams carry silt particles, and all of the mountains are slowly weathering down via water, transporting the small particles that are being weathered out to the ocean. And streams being higher energy environments, but the ocean is a relatively low energy environment. Now I'm not thinking of the tides and the waves. That's clearly an energetic environment. But the ocean overall, once you get below wave base, is a very low energy environment. It's gravitationally stable. It's the lowest that it possibly can be. It can't really get any lower, right? Water particles can't really go any lower than the depths of the ocean. A delta is a geologic deposit of different types of, or different coarsening of sediments. So you can have coarse defined sediments where the river is dumping its load into the ocean, and then it settles down to the bottom of the ocean floor. And then that pile of sediments piles up, and more keeps on a-coming, And that phenomena that dump of sediment is what's known as the delta. And it forms a triangle at the mouth of the river where the river is leading into the ocean. That tends to be a point source. But then all along the way, the whole triangle is kind of filled in by the rivers meandering back and forth and dumping their sediment load over here. And then it kind of gets full, so it meanders over here, and then it gets full and goes back and forth. So it tends to be a triangle shape, or the Greek letter delta. So known as deltas, these areas that receive sediment from rivers. Well, what happens if you put a dam on a river then? Well, all of that sediment builds up behind the dam. That's the siltation of dams, and why they only have a kind of a finite dam lifetime is the silt that builds up behind them. And if you dam all the silt, well, then all the deltas are being starved of all of that silt. So one of the factors leading to sinking deltas globally is that they're being starved of their sediment. So a delta is an active sedimentary deposit. If there's no more coming in, it's going to keep sinking under its own geologic processes, but it's not filling in on the top. So that's one reason. Then those deltas, the reason they sink under their own sort of geologic processes is kind of twofold. One of those is called subsidence, and then another, sediment compaction overall. So the sediments at the bottom are becoming more and more compacted by the stuff at top. Even if you have less stuff that's coming in, this weight, the gravity of below, is still allowing these to compact. So if the deltas continue to undergo sediment compaction naturally, but no influx of new material, then they overall sink. Well, what about compacting non-naturally, right? So we do that also. We actually compact the sediments by living on them or adding infrastructure to them. So the Ganges, Brahmaputra delta into the Sea of Bengal, I think, that river not only is it starving of silt, but also that delta, close to 500 million people live on or near deltas overall. And on the Ganges, Brahmaputra, in Bangladesh, millions of people live in cities on this delta, not necessarily on the active geologic part, but on parts that are older as sea level has dropped since then and left this perched delta behind, or areas where the delta has prograded out into the ocean. So, but it's all still part of the relatively recent geologic delta. So we're compacting it, but not only that, we're also taking stuff out from down below. So we take oil and natural gas that form on those swampy environments at the delta margin, and also just fresh drinking water, right? Those are aquifers that we can pull water from. So we're pulling out water, we're pulling out gas and oil from those areas that leads to the overall compaction by that removal. Trapping the sediment in reservoirs upstream, and then top it off with overall a rising global sea level. So there are multiple geologic factors involved. Mostly, all of those caused by human factors, global sea rise by melting sea ice via global climate change, via increased carbon dioxide amounts in the atmosphere, by energy consumption. Then the trapping of sediments by building of dams, the compaction by living on them and having gigantic cities on them, and the removal of oil, gas, and water that leads to that compaction. So to round that out, what this slide and what I'm saying here is that geologically we are a force to deltas. Deltas look different in the Anthropocene than what they looked like in the Holocene. Different. We've changed the shape of those. We've changed how they evolve through time. And even if we stop doing it tomorrow, all the dams just go away, all of the cities that are living on these, no more oil and gas. If we just stop tomorrow, it isn't going to change. It's not like they're going to rebound back to what they looked like in the Holocene. Those things will stay, and we will see them geologically in the future. And here's a number of these deltas that are going through this process actively. Okay, back to biology. I should have slid this slide up a little bit further, but this falls under the modern category of how we're perturbing the biosphere. So again, coming back to the biosphere, is that there are several species in our time that have gone extinct, or if you refer under our watch, right? If we're and again, we have this ingrained idea from thousands of years ago that we were sort of imbued with these qualities as being the stewards of the earth, that we are the overlookers, that we are the caretakers of this whole thing. But even with that mentality, we haven't been the greatest of caretakers. Under our watch, there has been dozens of species that have gone extinct because we have driven them to extinction, either exclusively driven them to extinction, not unlike the overkill hypothesis. So things like dodos that are really easy meat to get to, or we have changed their environment so much that their population is no longer sustainable, and they have gone extinct. So what those last couple slides were showing and demonstrating was that we have influence on this marker bed of geology. Okay, so without in the last lecture, it was shown, we have roads, we have electricity, we've, of course, detonated nuclear devices that have changed the chemistry of the atmosphere. But those last couple slides specifically, I wanted to show you how the fossil assemblages change. There's more chickens. There's more plastics. How the sediments of deltas change through time. How weathering rates have changed through time. And then also, one I should have also added this, is that we are a geologic force that moves more sand, rock, and gravel than all of the world's streams and glaciers combined. So we move more material than nature does itself these days. And of course, we looked at this the other day. All of these trends that are upticking, these are the Earth system trends. So you might as well put things like the biodiversity loss or extinction rates on here as well, that also increase as we get closer to this time. Now notice some of these begin to increase before 1950, and that's what I referred to earlier as kind of the pre-Anthropocene. There was this end Holocene industrial era, right? I mean, we entered the industrial era with the steam engine and coal, and we were beginning to perturb the environment and to globalize a couple hundred years ago. So some of these natural environment trends, of these earth trends, were already on an uptick. It's just that we really turned the burner on, or really started to cook this stuff when we discovered oil in the late 1800s, and then began to distribute that more widely. And after World War II and all of the technology into that, we were able to really change our world to be a scientific, very exclusively scientific world, and do everything in our power, to not die and to be able to feed ourselves and to get to where we want to go. Now, of course, those three things aren't universal throughout all of humanity, right? There are plenty of starving people. There are plenty of people that are dying and that can't get to where they want to go. So there's, of course, a major geographic divide of these things as well. So in other words, to say these trends are not universally every human being's fault, right? We all weigh into these things at slightly different amounts, right? Some of us, and I don't love the term carbon footprint, but some of us have a much higher carbon footprint than others of us, particularly globally in different countries. So there's the Earth trends and then the socioeconomic trends again. And I want to focus a little bit more, not really focus on this one a bit more, but I blew it up this time so you could really see urban population in general, energy use, water use, paper production. They all follow a really steep trend where starting at the 1950, different than the Earth systems trends. As I said, we were changing these systems slowly over the last couple hundred years, and some of them were already on a natural trend as well, like warming. We are in an interglacial. The glaciers have been receding for the last 11,700 years, so it is not solely our fault that glaciers are receding. That's what they were doing. But we have extremely quickened that pace by our activities in the last couple hundred years. What's different here is that almost all of these things begin their major rise slightly preceding the 1950 event. So population, urban population, so on and so forth. So that's something slightly different, and why we would choose the mid-21st century to show, or 20th century to show the Anthropocene. All right, this is one of my my favorites from geology class overall, is the discussion of resources. Every American born, this is called the Mineral Baby from the Mineral Education Coalition, every American born in their lifetime will use an estimated 3 million pounds of minerals, metals, and fuels in their lifetime. And here's those kind of calculated amounts. And these are averages, right? Again, we all use a different amount of materials, but average, if you drive on roads, if you eat food, if you go live in buildings that are warm, stuff like that, then this is a good average for all of us living in America anyway. Also, an American-based government agency, the USGS, the United States Geologic Survey, back in 2001 launched the Global Mineral Resource Assessment, saying, quote, "It's time to know the planet's mineral resources. Science for a changing world." We are in this Anthropocene. This was well before the Anthropocene was really a hot topic of discussion, but we know that we need to be looking forward in a different way than the people 1,000 years ago were looking forward, right? We really need to be looking out for the future generations with the amount of consumption. So this is very interesting. The copper assessment was one of the first that was complete, and this is an excerpt from that study. 225 areas for undiscovered copper in 11 regions of the world. So there's still yet targeted areas where we know it probably exists, but we don't know if there are deposits there, how big they are, how concentrated they are, stuff like that. But there is more that can be explored. The amount of undiscovered global copper estimated by the USGS would be enough to satisfy current world demand for more than 150 years. Of what we know we have, which is the stuff that's being mined out, that's the discovered stuff, and the undiscovered estimates, we have quite a couple hundred years. I almost said quite a long time. Remember, geologically, a couple hundred years isn't all that long. In even human history, that's not all that long. So from estimates like this and an understanding like this, we are really getting a better understanding of our longevity as a species and how needed it is for us to transition to becoming a sustainable species, or at least a species that can sustain ourselves by doing things like this, by recycling. So copper, it is argued, and here's the link to this article, it's argued that it is one of the most reusable or recyclable metals that is out there. And if we keep these metals, particularly metals, plastics are really hard to recycle because they downcycle through time. They get worse and worse and worse through time. But metals don't change. These are just things from the periodic table, and we can recycle and recycle and recycle and reuse and reuse and reuse. So as long as we keep copper out of the landfill, and all other metals out of the landfill, and we keep recycling them and reusing them, then these estimates become a lot greater, right? So that's the really key with things like metals.